Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking now at Chapter 8, which is Modeling Phase Equilibrium for Pure Components. We will not be doing all of this chapter, but we're going to be getting started and getting you ready for Thermo 2. We are looking now at two-phase systems. And for most of our properties, the change in that property is going to be most significant for the vaporization process. Okay? Now, the second law tells us that all nature is moving to a maximum entropy. So we shouldn't exist. We should all be a gas, right? Okay, but we also can show that the second law leads to nature moves to minimum energy, which would also imply that we're all dead, okay? But we know that we can beat that system because clearly we're all alive and well. How on earth does this happen? How can we model that? Those are the kinds of issues that are discussed beginning in Chapter 8 and that you'll be looking at more of in Thermo 2. Okay, so Gibbs energy is the energy function that is a function of pressure and temperature. It's a combination of energy and entropy, defined as H minus Ts, and our fundamental relation for that is dG equals minus SdT plus VdP. Vapor pressure is going to be the relationship between pressure and temperature along this vaporization curve. So P will be a function of temperature here. Delta G is going to be 0 for that. Okay. How can we use this to model what's happening in vaporization? So during a phase transition, the Gibbs energy is going to remain constant. So delta G will be 0, or dG is 0. So if you have two phases that are at equilibrium, and delta G is 0, then those two phases must have the same molar Gibbs energy. G for phase alpha and G for phase beta will be the same. Or if we look at little incremental changes in temperature, dG for alpha will be the same as dG for phase beta. Now we've got those fundamental relations. So this tells us that V times dP at saturation, we're talking about saturation or vaporization here, minus S times dt for phase alpha will be exactly the same as for phase beta. And fortunately, I can use algebra to combine these to solve for dP of vaporization, dP sat, divided by dt. And what we find is that this is equal to S for phase beta minus S for phase alpha divided by V for phase beta minus V for phase alpha, or more simply, delta S for phases alpha beta over delta V for phases alpha beta. These are the changes in entropy and volume per unit mole as we go through the phase change. Now, entropy is always a little distressing when I see that show up in an equation, right? But if we integrate this at constant temperature, the latent heat of or the latent enthalpy of phase transition is going to be delta H equals T times delta S. If I substitute that back into the previous result, then dP dt for vaporization is delta H for the phase change over T delta V for the phase change. So I've eliminated the delta S by using the definition that it's delta H is T delta S. This is the Clapeyron equation. It is not specific to vaporization. this could in fact be used for any phase transition, okay? But let's look at this for vaporization because that's the one we're concerned about today. So dP vaporization dt is delta H of vaporization over T times the volume change as we vaporize, the difference between saturated liquid and saturated vapor volume. But, we know some stuff. And first of all, delta V is going to be V for the vapor phase minus V for the liquid phase. And so that would be RT over the vapor pressure times the Z difference between those two. Okay. And if I plug those in here, I get dP dt is the vapor pressure times delta H of vaporization over RT squared delta Z. And we can rearrange this to group my pressures together. And dP over P is the derivative of log of P. Do you agree with that? So the derivative of the log of P dt is delta H of vaporization over RT squared delta Z for the phase change. And okay, so now then how about my T's? I've got dt and I've got T squared over here. So if I bring this to this side, dt over T squared, that is the same as the differential of 1 over T. So now I can say that the derivative of the log of P vape is over D, the derivative of 1 over T is negative delta H of vaporization divided by R times delta Z for my phase change. Okay? I haven't done anything here except for play with some algebra games and some calculus definitions. But I can make some simplifications, and we're going to develop the Clausius-Clapeyron equation. Now this says, wait a minute, you know what? Most of the time, I don't need that complicated stuff. I can make some really great simplifications. First of all, if the vapor phase is very nearly an ideal gas, and I see that I typed 1 and 0 in there, but ZV is about equal to 1, okay? So the Z for an ideal gas is 1, and if my vapor phase is low pressure, and when I have two phases, usually it is low pressure, so Z for my vapor phase will be approximately 1. The liquid, on the other hand, it's going to be small. Okay, it may not be 0 small, but it's a lot smaller than Z for my vapor phase. And so therefore that delta Z I can replace with just 1. So this makes my equation a lot easier. The heat of vaporization is equal to negative R, the derivative of the log of vapor pressure, divided by D over 1T, 1 over T. And I can integrate that and get this relationship here. This is the Clausius-Clapeyron equation. And it's very important in estimating vapor pressures. So we've made one assumption, and that is that the vapor pressure is going to typically happen for low pressure systems. So therefore the gas is nearly an ideal gas, and the Z for the liquid is going to be much closer to 0, and so therefore I've eliminated the delta Z term. So I did that. I also did one other thing that I didn't mention as I did it, but when I did this integration, I assumed that delta H vaporization was constant. So this is approximately constant, and ZV is about 1, ZL is close to 0. So those were the assumptions that went into this. Otherwise, I got to go back to the original Clapeyron equation. If I wanted to use this to estimate, say, the vapor pressure of benzene at 50 degrees C, using this equation, all I need to know is the vapor pressure for something at any other temperature. Well, if you look up in the back of the book, you can see that the vapor or heat of vaporization for benzene is 33.9 kilojoules per mole, and the vapor pressure at 0 degrees C is 24.2 millimeters of mercury. So all I need to do is substitute these values in. So I'm looking for P2 sat. P1 sat is this 24.2 millimeters of mercury. Heat of vaporization, 33.9 kilojoules per mole. But my R value that I had was in joules per mole, so I converted this over, so 33,900 joules per mole. R, 8.314 joules per mole Kelvin. My temperatures, I have to be sure I'm using absolute temperature. So 1 over T2, which was 50 degrees, minus 1 over T1, which was 0 degrees. I'm able to estimate that the vapor pressure should be around 244 millimeters of mercury at 50 degrees C. So this is using the Clausius-Clapeyron equation, but this is not the only way to estimate vapor pressure. So we'll be looking at other techniques in our next video. Thank you very much for your time.